Hello, this is lesson 2 of our remote learning programme for Group 7, the halogens. In the first lesson, we looked at some of the key trends in Group 7, a good chance to remind ourselves of some of the basics on periodicity, and also looked at the oxidising ability of the halogens. Today we're going to move on and look at reducing ability within Group 7 as well. So, as always, I'm going to recommend that you pause when you get to a task, and only when you've completed that task, go on and review what you've done. Then you can identify any questions you need to ask, and then you can get the support that you need to build improvements in where it's maybe not quite clicking into place yet. So we're going to take a look at reactions of the halide ions, trend in reducing ability, linking it to ionic radius, and looking at observations and tests for halide ions using silver nitrate. That part will be familiar from GCSE. So have a think about these two questions in task 5, and when you're ready, move on. Okay, so if we take a look at task 5, what is a reducing agent? I'm not going to jump straight in and tell you what it is. I'm going to develop the idea so that you've got a link, a way of working your way through to it, so you're not just remembering it as a fact. So the first thing to consider is that a reducing agent is itself oxidized, and we know that oxidation is loss of electrons. Now, when we're talking about a reducing agent, we need to talk about it in that context. So rather than losing an electron, it's donating the electron so that something else can be reduced. Now, in terms of what you think the best reducing agent is from Group 7, and we're only dealing with periods 1 to 4, so only going down as far as the period containing iodine, which do you think is the best reducing agent? And I'm going to ask you to really hold on to the idea at the moment. And I'm going to ask, have you picked fluorine, chlorine, bromine, or iodine? Well, I am going to start going through and I'm going to build to the right answer here. If you said iodine, you're incorrect. If you said fluorine, that's at the opposite end, you're incorrect. So you might now be looking at it thinking, okay, it's bromine or it's chlorine. No, all of those are incorrect. And it's an annoying question. I'm deliberately being a little bit irritating here because I want to point. Halogens are oxidizing agents. If we are talking about the best reducing agent in Group 7, we need to talk about the halide ions. Because the halide ions are the things that can be oxidized. They are the things that can lose electrons to go back to their atomic form. So once you've got these four, once again, have a think, if you hadn't already made up your mind about one of these, which of these is the best reducing agent? And the correct answer is the iodide ion. So well done if you said that. If you didn't, don't worry, because we can start to explain why that is the case. So we're going to begin by looking at the fact that the iodide ion is larger. If it's larger, the outer electron is further from the nucleus. And it's also subject to more shielding. We're seeing these similar themes coming through again and again and again. Now, if the outer electron on an iodide ion is further from the nucleus and subject to more shielding, then it's going to be more easily lost. If it's more easily oxidized, that makes it a better reducing agent. Now, when we investigate the reducing ability of halide ions, we do it using sulfuric acid, specifically concentrated sulfuric acid. Now, I've made this point here. There is nothing wrong with the way that textbooks do this, where you learn key facts and you learn equations and you write them down from memory. But I'm going to approach it in a different way. I'm going to approach this in a way that utilises the skills and knowledge that you've developed in the rules of redox, in determining oxidation states, building half equations, combining half equations. And so I want you to bear that in mind as we're going through. The videos are available to go back through that topic if that's something that you feel that you would benefit from. But let's get started. In all of the cases, we start by taking the solid sodium halide and we react it with concentrated sulfuric acid. And in every single case, we get this same reaction where the X is substituted with a halogen. So what I would like you to do is write out that equation for each of the sodium halides that we have here. And then I want you to think about what has been oxidized and what has been reduced within that reaction. So pause it, try to write out the equations, and then work out what you believe has been oxidized and reduced. Taking a look at the equations, hopefully relatively straightforward. We had the NaCl instead of NaX and HCl instead of HX. Repeat the same thing with the HBr. Repeat the same thing with the HI. So the equations themselves, this is the start point for every single reaction between the sodium halide and concentrated sulfuric acid. Let's start to take a look at the oxidation states. Well, in every single case, sodium has remained +1. It's in a compound, and group 1 elements will form ions with the charge of +1 and have an oxidation state of +1 in a compound. If we then consider the halides, they have remained as -1. They're all in group 7, they're all combined with either an Na plus or an H plus, so they have not been oxidized or reduced either. So let's move on and let's take a look. The hydrogens, well, they're all +1 in every single circumstance. So we've got the S's, well, the S's remain +6 if you work out the oxidation state of them. And just to double check, we're going to go to the oxygen as well. The oxygens have all remained -2. Nothing has been oxidized, nothing has been reduced. And that will always be the case in stage 1 of this reaction. So if I did this, I would make white fumes in every single case. The white fumes are the HCl, the HBr, or the HI. And then there's this tiny bit at the bottom that I'm just going to highlight. The reaction with NaCl stops at this point. Chloride ions are very poor reducing agents. They cannot reduce sulfuric acid any further, so the reaction stops. And that is something you would need to remember. The observation would be HCl, the equation is as we've written on the top line here, and nothing else would happen. But we're going to go on and consider the reaction with NaBr. And I want you to work through this as best you can. I want you to use your knowledge of building half equations, and then we're going to take a look at it once you've given it a try. Okay, so let's look at the oxidation state of sulfuric acid. Well, hydrogen is +1 in a compound unless it's in a metal hydride. This isn't a metal hydride, so it's +1. Oxygen is -2, apart from in a peroxide when it's -1. This isn't a peroxide. So I have got -8 and +2, and I need to get to an overall charge of 0. So my sulfur must be +6. In SO2, my two oxygens are -2. I need to balance my overall charges and oxidation states to equal 0. So in this case, the sulfur is +4. Now we need to build the half equations. So I'm going to go through this step by step, following the rules, and I'll remind you again, if you're unfamiliar with these, I have made the redox topic available to you to go through in a bit more detail. But we'll start off with reducing sulfuric acid to SO2. Now, the first rule is you balance the species with a variable oxidation state. That's the thing that's not hydrogen or oxygen. the sulfur is already balanced. The rule 2 is that I balance the oxygens by adding water. I've got 4 oxygens on the left, I've got 2 on the right, so I need 2 H2Os to balance those oxygens. Rule 3 is the balancing of hydrogen ions, or the balancing of hydrogen, sorry, and we balance hydrogen by adding hydrogen ions. I've got 2 hydrogens on the left, I've got 4 on the right, so I need to add 2 H plus on the left hand side. And the final rule, rule 4, is you balance the charge by adding electrons. Now my total charge on the left here is +2. My total charge on the right is 0, so I need 2 electrons to balance that out. Slightly more straightforward half equation with the bromine. Rule 1, balance the species with the variable oxidation state. In this case it's bromine, and I do need 2 bromide ions on the left hand side. I don't have any oxygens to balance by adding water. I don't have any hydrogens to balance by adding H+, so I get to rule 4 and I balance the charge. And I'm going to do that by adding 2 electrons on the right hand side. Now once we've built the half equations, we can combine them. And I'm going to combine them by following the rules. And again, the rules are available on the redox videos that are also available to you in more detail. But I've got 2 electrons on the left and 2 electrons on the right. So I then combine everything on the left and everything on the right to give me the full equation. I'm then looking for spectators, things that appear on both sides that have no overall part to play. And I can see that my electrons appear on both sides, so I can get rid. And that allows me to simplify my overall equation, my whole equation, in this way. It can be written in a different way as well. You can write HBr. And remember, you made HBr in step 1 of this process. So the H2SO4, the conc H2SO4, is now reacting with the HBr that we made. Now, when you look at this and you're considering the observations, yes, we've got white fumes of HBr, but that won't be the only observation here. Look carefully at the products and decide what else would you see. And what I'm hoping you recognised is we've made bromine, and with bromine we would get brown fumes. Now, if you are equipped to build half equations and combine half equations, the only thing you actually have to learn here is that bromide ions can reduce sulfuric acid to SO2. The rest can be done by utilising those skills. Let's move on and let's look at NaI. Now I've just spotted a typo here. It should say iodide ions. As if by magic it now does say iodide ions, but they are better reducing agents, as we established earlier. They can reduce sulfuric acid all the way to S. They could even take it all the way to H2S. And when you look at that, we're seeing the oxidation state of the sulfur going down from +6 to 0 or even -2. Remember, chloride ions could not reduce it from +6. Bromide ions could only reduce it to +4. Now, I've given away a little bit of the answer here. It will say bromide on the future slides, but remember, this is iodide ions that we're talking about. So let's look. Oxidation state of sulfur in sulfuric acid. Well, we did that one earlier, +6. In sulfur, it's 0, because the oxidation state of an uncombined element is always 0. And in H2S, I've just mentioned it, but we can see I've got 2 +1s from the H's, so the S must be -2. Now, I've already talked about the answer to this question down at the bottom, so hopefully you are able to verbalise this in your own way. Hopefully you've already tried to answer this question. The Br- ions can only reduce sulfur from +6 to +4, whereas the iodide ions can take it all the way down as far as -2. So we're going to take a look at half equations and combining half equations. Slightly more complicated this time because we've got 2 alternatives for what happens with iodide ions. There's technically 3, because iodide ions can reduce sulfuric acid to sulfur dioxide as well. It's important that we focus on the fact it can go further to the sulfur and to the H2S. So let's write out these 3 half equations. I minus going to I2. I balance the species with the variable oxidation state. In this case, that's iodine, and I do need to balance it. I have no oxygens to balance. I have no hydrogens to balance. So my next thing is to balance the charge. I do that by adding electrons. I add 2 electrons on the right-hand side. Moving on to B, H2SO4 goes to S. My S's are already balanced. So I balance the oxygens. And to do that, I add water. I need 4 H2O on the right-hand side. I then balance the hydrogens. At the moment, I've got 2 hydrogens on the left and 8 on the right. So I'm going to need 6 hydrogens to balance those out. And finally, I'm going to balance charge, and I do that by adding electrons. My total charge on the left is +6. On the right, it's 0. So I need 6 electrons on the left to balance those out. For part C, similar idea. H2SO4 goes to H2S. The S's are already balanced. I need 4 H2Os to balance the O's. This time I need 8 H pluses to balance the hydrogens, and now I need 8 electrons to balance the charge. Now in the first instance, you're then being asked to combine equations, or half equations, A and B. And in A and B, you can see that actually I'm going to have to multiply A by 3 so that I've got 6 electrons on the left and 6 electrons on the right. The electrons have to cancel out. So if I'm multiplying A by 3, I have to multiply it all by 3. And that's why I've got 6I minus and 3I2. Now I can get rid of my spectators and I can rewrite my full equation. And once again, similar to what we saw with the HBr, you could write the 6H plus and 6I minus as 6HI. We're then thinking about what observation you would make in this case that's different. Have a think about it if you haven't already. Jot down some ideas. And I'm hoping you've come up with more than one, because 2 of the products here are going to give us a good observation. In the first instance, we're making sulfur, which is a yellow solid. So we would see yellow precipitating out. But we're also making iodine. Now, iodine is a blue-black solid, but it very easily sublimes into purple fumes. It's a molecular covalent crystal, so it has low melting point. Low sublimation point technically, but it will sublime into purple fumes. So I've got 2 different observations to remember here. Now, you could learn every single fact on here, or you could learn that sulfuric acid could lead or could be reduced to sulfur by iodide ions. And then you've got to remember the observations for the products that you would recognise as you built the half equations as we've done here. Because now we need to move on again, and we're combining equations A and C. Now you can look back, you can go back on the video, or you can look back at your notes in the booklet, but this time we needed to multiply the I minus half equation by 4 to get to 8 electrons. Because we've got the same amount of electrons on each side, which is really what we're aiming for, we can get rid of those as spectators. So that allows us to write the full equation as we have here. Now, as we saw earlier, that could be summarised to 8HI as well. I'm just not going to squeeze it in to that space. Now on here, we're thinking about the further observation. We already know about iodine. We know about the purple vapour or the blue-black solid. But what other observation might we make here? Well, actually, it's all about the H2S. The H2S is actually used in stink bombs. It has a rotten egg smell. It has a pungent aroma. So for this one, you would need to know that we can reduce sulfuric acid to H2S if we use iodide ions. and that we would make H2S and what the observation would be. Now, I'm going to move on to try to summarise the key facts that you need to learn. And if you learn the facts in this table and combine that knowledge with your ability to build and combine half equations, this becomes a much more manageable topic. So have a go at filling this in. You've got space to change it in different colours if you need to later. You can make corrections, but try it and see how you do. Okay, let's review it. So the product in the initial reaction of solid NaX, remember that's the thing that happens in every single iodide. We end up with NaHSO4. We've swapped an H for the Na. And then we make the hydrogen halide, HCl, HBr or HI. So now, if you need to, have a think about the observations. What would you see in each of these cases? And hopefully you're remembering from what we've spoken about earlier in the video, white fumes in every single case. At this point, the table becomes a little bit more manageable because we know the chloride ion reaction has stopped. Nothing further happens because it's the weakest reducing agent of the three that we investigate, and therefore nothing more happens. But actually, we can then think about what happens with the bromide ions. And we know that if I use bromide ions, it can reduce the sulfuric acid, which means we will make Br2. And we have to remember that Br2 will be observed as brown fumes. And we also have to remember that the sulfuric acid can be reduced to SO2. Now, I've not spoken about the observation of this before, but I've put it into the table. SO2 is an acidic choking gas. It's not necessarily one that you're going to talk about in great detail, and that is purely because it's not a clear observation. Some of the others are much more obvious. So let's move on to the iodide. Well, we know the iodide will be oxidized to iodine when it's acting as a reducing agent, and we know that that will be a blue-black solid or a purple vapour. And we also know that it's capable of taking sulfuric acid down to SO2, but beyond. It can make S, or it can make H2S. So, if it made SO2, it would be the acidic choking gas that I've spoken about. If it went as far as S, we'd get a yellow precipitate, and if we went as far as H2S, we would end up with a rotten egg smell. Now that takes us to the end of this lesson, and I think that the volume of content that we've gone through is absolutely huge. I don't think this is something that makes sense necessarily the first time you do it. And the key to success is going back and practicing building the right half equations, knowing what each halide ion can take sulfuric acid down to, and then combining those half equations and then recognizing what the products are and what observations you would make as a result. Hope that's been useful, and I will see you next lesson.